Greetings and salutations, magical chemists. Let's talk about another application of IMFs, heating and cooling curves. First, this is a great opportunity to review KMT, kinetic molecular theory. This is based on the idea that particles of matter are always in motion. We often talk about KMT for gas laws, but technically it can be applied to other states of matter as well. So let's talk about how IMFs apply to changes of state. Now, of course, if particles are in the gaseous state, they have complete freedom of motion. This means that their high amount of kinetic energy overcomes the attractive forces between the molecules. In fact, you may or may not remember that one of the postulates of KMT states that gas particles have no attractive forces. That's because of their high kinetic energy. Okay, if you instead think of the liquid state, well, in the liquid state, particles have limited freedom. They can move around a little, but within the liquid, of course. In the liquid state, they have enough kinetic energy to overcome some of the attractive forces, but not enough to escape each other. And in the solid state, of course, particles are locked in place. They cannot move around relative to each other. Now, the particles in a solid are indeed vibrating, but they don't have enough kinetic energy to overcome any of the attractive forces. What's interesting to note that the strength of the attractive forces between particles of a given substance determines its state of matter at a given temperature. At room temperature, substances with moderate to strong attractive forces will be materials that are solids or liquids. And of course, the stronger the attractive forces, the higher the boiling or melting point will be. So the table below gives a nice kind of comparison between the states and just kind of summarizes all this information. Of course, a gas, which has an indeterminate shape and volume, has really weak IMFs relative to its amount of thermal energy. A solid is the opposite. It has a definite shape and a definite volume, and of course it has strong IMFs. And a liquid, is in between. So we can apply these concepts by looking at heating and cooling curves. Well, heating and cooling curve is one curve, but So here is the thing. This, of course, is water. Classic. You may or may not recall from our unit on thermochemistry, but there are going to be three particular parts of the graph where you are changing the temperature. You're either heating up your solid, this first slopey part, you're heating up your liquid, the second slopey part, or you're heating up your gas. However, there are also two plateaus. These are the changes of state. So the first change of state, of course, where this plateau occurs is the melting point. So this is the energy it takes to transform from a solid into a liquid. And then, of course, there's also the boiling point, the temperature at which it takes to transform from a liquid into a gas. Notice, during a phase change, it is a plateau, it is flat. The temperature, and thus kinetic energy, is not changing. All the energy that you're applying during a phase change goes into overcoming the intermolecular forces. So the potential energy is changing, but not the temperature. Now, I know we've looked at heating and cooling curves before, but okay. So in thermochemistry, our focus on heating and cooling curves was how much heat energy was required to change from one state of matter to another. That's where we're using MCAT or the Na and delta H equation. For this unit, however, our focus is on two things. First, the relative amount of kinetic energy for each state of matter, and, of course, the strength of the intermolecular forces holding the particles together. So let's just try a quick particulate representation practice. So if liquid nitrogen is shown in this lovely image over here, which of the images below depicts nitrogen after it has boiled? I would, of course, like you to choose the correct answer, and when you're ready to check your answer, well, you know what to do. If you picked D, you win, because remember, when boiling, you haven't broken any chemical bonds. They're still diatomic, but now as a gas, they're very separated. There's lots of empty space between them. Good work, magical chemists. All right, you have one last video to go. We're going to talk about IMFs and solubility, and I'll see you there.